So hopefully you have been following along and doing a good job of sort of trying to understand each of the parts. Right now we're going to put everything together in a hypothesis test for proportion. So we're going to go through all of the steps and we're going to do 2 examples. So first is the steps. So of course the step first is to do the model, which of course includes checking conditions. So I'm going to list and check all the conditions: independence, randomization, 10%, and success fail. And then I'm going to state the model, which is the normal model, and the test, which is a 1 proportion z test instead of a 1 proportion z interval. Then I'm going to write the hypotheses. So the null hypothesis we just talked about is h sub 0. Then p is whatever I think it's going to be, and then talk about it in words. The alternative is either going to be not equal to, less than, or greater than. And then again, write the alternative in words. Notice that the values here, though, the hypothesized value, that's the same value each time. Then I'm going to do my calculations. You should draw yourself a curve. This is not something you'll have to submit, but you'll want to think about, am I going to the right, to the left, or is it two-tailed? And of course, that all depends on what the alternative hypothesis is. So if I'm looking for a greater than, then I would draw a curve and shade to the right. If I'm looking for a less than, draw a curve, shade to the left, etc. If it's two-tailed, remember that's the one that looks like this, where I'm just saying it's different, so I'm shading on the outside. Then I'm going to calculate all of the things that I need to calculate. Now, you can either calculate the z-score kind of all together, and if I did that, it would look like z equals p hat minus p sub 0. Now, p sub 0 just means this is what my null said it's going to be. P hat is still my observed value. And then I would just include this, which is my observe or my null value, p sub 0, q sub 0 over n. So again, notice when I'm doing a hypothesis test, I'm using the standard deviation. When I did the confidence interval of the same kind, I used the standard error instead. But I'm going to actually use my hypothesized value for both p and q. And then I'm going to find my p-value, and I'm going to use my normal CDF or StatCrunch to do so. And I'll show you at the end of this how to save yourself from having to do all of this stuff in the middle, because we'll be able to do calculations completely using technology. But a few more times we're going to do some checking with by hand, of course. Then we write our conclusion. If our p-value is smaller than the alpha, then we're going to reject the null. So because p is whatever is very low, I reject the null hypothesis. There's strong evidence that the alternative is true. But remember, I want what is the alternative, etc. So we're going to do one of these. I'm not going to say that it shows the alternative is true. I'm going to talk about what is the alternative here. Same thing, because the p-value is high, I fail to reject the null. There's insufficient evidence to suggest that the alternative is true. So let's take a look. Example 1. U.S. Consumer Report claims that 90% of all American homes have smoke detectors in them. So right away you should think, okay, is that my P or is that my P hat? Well, this is what I'm going to assume is correct. So that's P. That is the P sub 0, if you will. It is the population, the hypothesized proportion. So Omaha wonders if their efforts to educate the public about smoke detectors have moved the local level to be above 90. So above 90 is very important because this is going to tell me what to do with my alternative hypothesis. Building inspectors visited 400, that's N, they visited 400 randomly selected homes and found that 376 had smoke detectors. 376 isn't anything, but P hat is going to be 376 over 400. And then, is this strong evidence that the local rate is higher than the national rate? Again, the above and higher, that tells me the alternative. So step 1, of course, do the model. My conditions are the independent, so whether or not someone uses a smoke detector is independent by household. 400 homes is less than 10% of the homes in Omaha. Success fail, N times P. Notice here I'm not using the 376. I'm using N times my P, which is 0.9. So 400 times 0.9 is 360. 400 times 0.1 is 40. Both are greater than 10. And then randomization, homes were randomly selected. I think I went in a little different order this time, but it doesn't matter. Just make sure you get all 4. and then say, because the conditions are met, we can use a normal model and we will perform a 1 proportion Z test. So the conditions are met, normal model, what's the test that you're doing? Then I'm going to write my hypotheses. My null hypothesis is that it is in fact 90%, that nothing has changed, that I'm expecting 0.9, which means 90% of Omaha homes have smoke detectors. My alternative, the one that I'm actually testing, is based on the context. This says above 90, higher than the national rate. So my alternative hypothesis is that the proportion here in Omaha is greater than 0.9 or more than 90% of Omaha homes have smoke detectors. So those are the ones that I'm going to use when I do my calculations. When I do my calculations, I'm looking at 0.9 to be in the center. I found 376 out of 400, which actually turned into 0.94, so that is my p hat. So looking at my picture, 0.94 is to the right of that, and I'm looking for that or greater. How do I know greater? Because my alternative was p is greater than 0.9. So greater than this. This is 0.94 or more extreme. So what I'm going to be finding when I find my p down here is going to be the probability that if the actual proportion in Omaha is 90%, that my sample, that I would find a sample that had 94% or greater. So that's what I'm going to be finding. To do my calculations, I'm going to do my z-score, which is 0.94 over 0.9. 0.94, again, p hat, observed minus expected, which is 90%, over the standard deviation using p, 0.9, so 0.9.1 over 400, and then equals 2.67. That's my z. How do I find the probability? Well, the p-value is based on either using StatCrunch or normal CDF to find that 0.004. We already reminded ourselves how to do this last week, so hopefully you watched those videos. If not, I would go back and do that, because that's how we find that 0.004. Now, what's my conclusion? I'm looking at 0.004 and I'm comparing it, because it doesn't tell me the alpha level. I'm always using 5% or 0.05. So remember, if I get a value that is less than 0.05, then that means I'm going to reject the null. I'm going to say, hey, whatever I thought was going to happen, I feel like that was probably wrong. So here, the p-value of 0.04 is very low, making it unlikely that I would find the observed results by sampling error. So I'm going to reject the null hypothesis. Remember, the null was that p was equal to 0.9. That here in Omaha, it's the same 0.9 as it is across the country. So I'm saying, no, based on my results, I feel like that is not true. There's strong evidence that in Omaha, more than 90% of homes have smoke detectors. Notice that came from the alternative hypothesis. So I'm always talking about the alternative hypothesis in context based on whether or not I reject or fail to reject. So there's strong evidence that in Omaha, more than 90% of homes have smoke detectors. Based on that was my alternative hypothesis, and based on that's what I was testing. Oh, and notice that I didn't imply that it was because of Omaha's education initiative. I can't do that. Okay? There's no way to know for sure that that's why. Maybe we're just smarter here in Omaha. Now, we've already learned how to do a confidence interval. So what I want to look at then is what happens when you look at a confidence interval and the hypothesis test, because the conclusion that we come to, whichever one that you do, the conclusion should be the same. So this is the same exact question as before, and I want to find a confidence interval, and we're going to find a 95% confidence interval. And next week, we'll talk more about how to determine what level of confidence you should use based on your test. But for now, just take my word for it. We're going to do a 95% confidence interval. To do that, I'm going to do my p hat plus or minus z star times the standard deviation. Now, I want you to notice the difference though. When we did our hypothesis test, I used 0.9 here and I used 0.1 here. But because this is a confidence interval, remember I used the standard error, which is of course the square root of p hat q hat over n instead of pq over n. So I'm using the 0.94, the 0.06 over 400. When I do all of that work, here is my confidence interval. So if I were just doing a confidence interval, I would say I'm 95% confident that the proportion of homes in Omaha that have smoke detectors is between 91.7 and 96.3%. Now, what I was testing is there strong evidence that our local rate here in Omaha is greater than the national rate of 90? Do you notice that 90 is not in this interval? That my interval that I found that I'm 95% confident of is all greater than 90. So notice this does actually back up what I just found, which said I'm going to reject the null. I don't feel like the actual proportion of people here in Omaha is 90%. I feel like it's higher. And this is evidence that I'm expecting 91.7 to 96.3% of homes to contain smoke detectors. Now, this is how I would write it all together. So when you do your case study, you're going to back up, you're going to do a hypothesis test by hand, you're going to do a confidence interval by hand, then you're going to talk about whether or not the two agree with each other. So again, this is how I'd write it all together. This is the conclusion I'd written before with my hypothesis test. The p-value is very low, making it unlikely the observed results can be explained by sampling error. We reject the null hypothesis. There's strong evidence that in Omaha, more than 90% of homes have smoke detectors. In fact, I'm 95% confident that here is the proportion of homes that actually have smoke detectors. So notice I'm just writing it all together. That's how you'll do it for that final sentence. Now, I want you to try this one on your own. So I want you to do all of the parts. You don't have to back it up with a confidence interval, but I do want you to do the hypothesis test. So check the model, check the conditions, write the hypotheses, do your calculations, and write your conclusion. Once you've done so, press play to check your work and see how you did. So here we're saying there's supposed to be 20% orange M&Ms. So that's P. That's what I'm going to test. Is P equal to 0.2? Suppose a bag of 122 M&Ms has only 21 orange ones. Does this contradict the company's claim? So before I actually write my hypotheses, this does not indicate greater than 20% or less than 20%. So this is going to contradict. And to contradict the claim means that when I do write my alternative, it's going to be that it's not equal to 0.2 because it's not saying it's greater than or less than. But first, let's look at our model. So I'm going to look at the independence. M&M colors are independent. 10%, 122 is less than 10% of all M&Ms. Success, fail, I'm multiplying my values, saying they're both greater than 10. Randomization, they're put in the bags randomly and are representative of all M&Ms, and therefore the conditions are met, and I can use a normal model. I'm going to perform a 1 proportion z-test. Writing my hypotheses, my null hypothesis, H sub 0, is that P is equal to 0.2. So essentially I'm saying I'm expecting exactly what the company tells me, that it's going to be 20%. Bags of M&Ms contain 20% orange. My alternative is that it's not 20% because I'm just contradicting the company's 20% claim. So P is not equal to 0.2 and they do not contain 20% orange M&Ms. So notice I'm not saying it's greater than 0.2 or less than 0.2. I'm just saying it's not 0.2. Next, I have to do my calculations. And remember, my calculations would use this as my P. And so my calculation is, of course, starting with a z-score. And my observed would be the 21 over 122. That should go here. This is 0.172. So 0.172 minus my expected, my decimal in there, minus my expected of 0.2 divided by the standard deviation, which uses the 20. So 0.2, 0.8 over 122. So I'm going to do all of that to find my z-score. And notice that's exactly what I did. 0.172 minus 0.2 over 0.2 over 0.8. So notice that's exactly what I did here. I found my z-score, and my z-score was negative 0.77. Negative 0.77. But this one is actually a two-tailed test because remember my alternative hypothesis was that it's not equal to 0.2. So I have to do both sides essentially. Now the good news is this side is equal to this side. So I don't have to actually do the work twice. I just have to take it times 2. So I'm going to take 2 times the probability that p hat is less than 0.172, which is equal to the probability that p is less than negative 0.77, which I'm going to calculate in StatCrunch or my calculator. And then I'm going to take it times 2 so that it gives me this and this, because when I do that just the one time, it only gives me what's happening over here, which is the 0.22, which is actually 0.44. Now 0.44 is my p-value. 0.44 means 40% of the time, 44% of the time. If it's actually 20% orange M&Ms, 44% of the time I would get what I found myself, which is 17.2%. So 40% of the time, that's a lot, which means do I reject the null or do I fail to reject? Well, there's not enough evidence here to say that it's not 20%. So I'm going to fail to reject the null hypothesis. There is insufficient evidence. So I didn't find enough evidence to suggest that the proportion of orange M&Ms differs from the advertised proportion of 20%. So where did all this come from? This was my alternative, that p was different than 0.2. So there's not enough evidence. There's insufficient evidence to say that it's different.